Welcome. This video is going to start looking at the concept of equilibrium. For most of us, when we think of a reaction, we think of them as being complete reactions, meaning all the reactant gets converted to product. And the reality is this never happens. You never get 100% yield. And in fact, most reactions are considered reversible, meaning a significant amount of product breaks back down into the reaction. So we can speak of both a forward and a reverse reaction. Typically in industry, we write the reaction in the forward direction, with the forward reaction being the favorable one, the one we're hoping to maximize. So rate is how fast product forms. That's also referred to as kinetics. Kinetics mean movement. And equilibrium is the yield, or how much product is formed. So equilibrium state occurs when the forward and reverse reactions are happening at the same rate. So if you remember when we looked at reaction rate curves, we saw an exponential curve to it, whether you're looking at reactant decreasing or product increasing, and then there's a plateau, and that refers to the equilibrium state. The forward and reverse reaction are equal, so the concentration of product and reactant remains the same. So that means no net change can be measured or observed, but there's still change going on with the individual atoms. Some reactant particles are still being successful in becoming product, and some product particles are becoming successful in reverting to reactants. So a couple analogies: if you're bailing water out of a canoe as fast as the water is leaking into your canoe, or when you're running on a treadmill, you don't have any net movement, but you're certainly doing work. So equilibrium law uses concentrations and a constant called the equilibrium constant to try and quantify and predict the amount of product that should form. And in industry, of course, that's important because you're looking to make as much product as you can quickly at a low cost. Within our bodies, it's crucial to our health, such as the solubility of gases in your blood. You want to maximize the oxygen in your blood, but you want to minimize CO2 and other gases. Environmentally, it's important because pollutants are often caused by gases that maybe convert to other things. So a lot of areas where chemists are interested in equilibrium and yield. We could talk about equilibrium in physical systems like ice melting, water boiling, or in chemical systems. So to describe a physical system, bromine is a volatile liquid, meaning it easily evaporates, becomes a gas. So an open container at room temperature will evaporate, but if you put it in a sealed jar at room temperature, some of the molecules will turn to gas, but now the gas remains trapped in the container. So some of those gas molecules will lose speed when they hit the surface of the liquid or hit the side of the container, and they'll end up reliquefying. So initially you're going to see more liquid becoming gas, but eventually you're going to reach a state of equilibrium where the rate of evaporation and the rate of condensation become equal. And that's what the first and second diagram down here is showing you, is that initially when you seal the jar, you've got more of the liquid bromine becoming gas, but at some point that becomes equal. So phase changes can occur in physical processes, and slush was an example I mentioned. If it's 32 degrees out, you have both water and ice in a puddle, and you don't really know if it's freezing or melting. It depends on whether energy gets added or removed from that system to eventually push it out of that equilibrium state. And the same thing happens with chemical reactions. Some collisions result in product forming, while other collisions are going to result in the product reverting back to reactant. And again, when these occur at the same rate, we say the reaction is at equilibrium. So here's an example of hydrogen iodide dissociating to hydrogen gas and iodine gas. The hydrogen iodide and the hydrogen are both colorless, but the iodide gas is purple. So you'll know you've reached equilibrium when the flask quits turning darker purple and the color remains constant. And that means at that point all three gases are present, and their concentrations are going to remain constant because the forward and reverse reactions continue to occur, but at equal rates. So this is called a dynamic equilibrium and an equilibrium mixture. Dynamic meaning there's still change going on, but the net change is zero, so we can't detect the change. Macroscopically, we don't see a change, but if we could see it microscopically, there are changes going on. Also, it doesn't matter if you start with HI or if you start with the elemental hydrogen iodine. Either way, the equilibrium will be reached. It's going to be reached at the same rate and the same concentrations. And what I mean by that, if we look more closely at the graphs here, is in graph A, I'm starting with HI. I'm starting with the two elements, and they're decreasing over time, as we see here. And I'm producing HI. Well, if I look, the time at which equilibrium is reached is going to be exactly the same as if I had started with HI as the reactant and was forming the hydrogen iodide. And if you look, not only is it reached at the same time on the graph, but the amounts, if we extend across here, I'm not very good at my lines here, but the amounts of each component is the same concentration when we reach that equilibrium. So that's what we mean you can reach it from either direction. If I start with a specific amount of HI, it's going to yield X amount of H2 and I2. If I start with that X amount of H2 and I2 and let it run in reverse, it will yield that same amount of HI. It can be argued that all reactions go to equilibrium, but if very little product forms, we tend to call that a non-reaction. And if most reactant becomes product, then we consider it a complete reaction. So a non-reaction we indicate by putting NR and not even writing any products down, whereas a complete reaction we show by using a single arrow to the right. All other reactions, and the majority of them, are what we call reversible, and we use the equilibrium symbol with an arrow running both directions, or a double-headed arrow. So the forward reaction is looking left to right, whereas the reverse reaction is running from right to left. So looking at the graphs below, you can tell which reaction you're running, the forward or the reverse. The graph on the left, I see that the N2O4 is decreasing in concentration, so that must be my reactant, while the NO2 is my product. And on the right side then, the NO2 is decreasing, while the N2O4 increases. So now NO2 is my reactant and N2O4 is my product. For both graphs, it doesn't matter which direction you come from or what you start with, product or reactant. Equilibrium is the same, and the equilibrium concentrations are going to be the same. Increasing concentration won't affect equilibrium either. It'll just affect the rate and how quickly you reach that equilibrium. So equilibrium state is said to have 5 characteristics or features. First of all, it's dynamic, so both forward and reverse reactions are still occurring, but we can't see it on the macroscopic level. Second, it's achieved in a closed system. You're not allowing anything in or out of the system. No matter can come in or out. Even though energy can be exchanged, the amount of matter stays the same. Otherwise, it would shift the equilibrium. It would be like adding a product or reactant or removing one of them. Third, the concentrations of the reactants and products remain constant when you're at equilibrium. That's the definition of it, is that they're remaining constant. 4, there's no change in macroscopic properties, so we're not seeing a change in color or density that we can observe, but if we could see it microscopically, there is change, so that's why it's considered dynamic. And 5, it can be reached from either direction. It doesn't matter if you start with all reactant, all product, or some of each, you're still going to reach an equilibrium mixture at some point and the same concentrations, as long as you're doing it at a constant temperature. So equilibrium position then refers to the proportion of reactant and product in the equilibrium mixture. The proportion doesn't have to be 50-50. In fact, it rarely is. If the products are a much greater proportion, we say the equilibrium lies to the right or products are favored. And if the reactants are in much greater proportion, the equilibrium is said to lie to the left or reactants are favored. So we actually express this mathematically by calculating what's called the equilibrium constant, which roughly is looking at the concentration of your products over the concentration of your reactants. So you can see if the products are greater than the reactants, you'll have a Kc value greater than 1. But if the reactants have greater concentration, your Kc value will fall below 1. And again, equations are usually written with the preferred or intended reaction rate going in the forward direction. So usually we're looking for a large Kc or Keq value.